Okay, so hi, my name is Bihan Zhang. I'm a software engineer at Red Hat.
And I'm Dana Walker. I'm also a software engineer at Red Hat. This is my first convention and my first talk. Thank you. We work on the Pulp team, and we're going to go over ways to achieve reproducible environments for reproducible results.
So let's talk about reproducibility. What is it? It's making sure the same behavior is consistent through development, testing, and production. There's also the scientific sense in which you have to make sure results are replicable with the provided materials. There's a couple of different aspects to this. There's data, code, and environment. And this talk focuses on how to create replicable computational environments. And not only creating these environments, but doing so transparently and maintainably. Because if it's not transparent, it's hard for other people to set up. And if it's hard for other people to set up, you can probably never take a vacation ever. Maintainability ensures that once an environment is functional, it remains functional as time goes on. And we'll address each of these points through the presentation. So let's talk about what can go wrong when you don't have reproducible environments. So how many of you have ever had this conversation? Just having the same code doesn't mean two people are always going to get the same results. And there's a couple of different reasons why these two people might not be getting the same results. Same code, but a different dependency. Like she could be running SciPy 1.0, and he could be like still on 0.9. It could be that she upgraded her Python interpreter to 3.7, and he's still on 3.6. Or it could even be some system configuration setup. So there's a lot of possible subtle differences in every system. And the reason for these differences is because software is really complicated. So this is a dependency graph for Jupyter, GraphViz, and PipDepTree. The latter two are used to generate this dependency graph, and those dependencies are over there. The rest is all Jupyter. So how do you package your code when it has these complex dependencies? And how do you maintain your code once it's packaged when dependencies are updated? So let's talk about packaging real quick. Packaging, different ways of packaging addresses a lot of these issues. Packaging is tricky. It addresses messy problems, and every software ecosystem does it slightly differently. But let's simplify it a little bit and just talk about two high-level approaches. This is a monolithic package. Software is bundled with all its dependencies and released as a single package. This is great because you only have one thing to install, because all your code and all its dependencies are packaged together. So an operations person or a reviewer can just install that one single package. And because the dependencies are bundled, there's no chance that they will run into dependency conflicts. But monolithic packages are kind of large. This isn't bad, but it does make it really difficult to maintain. Because every time a dependency updates, in order to pull in that update, you have to repackage your monolithic package and re-release it. And this is a lot of extra work. And because this is a lot of work, it doesn't happen as often. So a lot of times you can fall behind on updates. It's also opaque. There's a lot of extraneous code and information in these monolithic packages. This makes review and testing, like the code that you write, more difficult. So monolithic style packaging is great for stability, but it moves slowly, it's not transparent, and it's harder to maintain. The modular approach is the opposite. Dependencies are handled at install time by a package manager. So you write your code, you specify your dependencies to Pygame and Matplotlib. Matplotlib specifies its own dependencies, and so on and so forth. This is the package management style of Linux and Python. So you guys should all be kind of familiar with it. It's great because maintainers don't need to rebuild their packages when dependencies are updated, because package managers pull in the dependencies automatically. It's a lot less code, so the code that you write is it's easier to test. And because your code does what your code does, and dependencies does what dependencies are created to do, and you have a separation of concerns. There are some cons to this. It does have a lot of install complexity. And because dependencies are resolved at runtime, things can go wrong. For example, dependencies can update, and then it could just break your code even though you didn't really update anything. And of course, dependencies can conflict, and you get into dependency hell. Dana's going to talk to you about how Python solves some of these issues.
So we're going to go over some useful tools for managing dependencies in just a second. But first, let's take a moment to go over the Python packaging ecosystem. In Python, packages can be found on the Python package index, or PyPI, not PyPy, PyPI, a repository hosted somewhere in the cloud. This repository is not curated. It has a series of guidelines for people. Anyone can upload it, their package to PyPI. But sometimes these people don't always follow the guidelines. It's possible packages can be deleted. You know, it's a very useful tool. And then these packages can be retrieved using pip. You can pip install these packages along with any designated dependencies. But what if you have two different projects you're working on at the same time, and they need different versions of the same package? Well, you can use virtual environments to keep these packages separate on your system, so that if, say, you had one project you were using that uses SciPy 1.0, and then you have another project you want to work on that uses SciPy 0.5, there won't be any conflict because they're in completely different spaces. There are tools and wrappers that work together with virtual environments to provide added functionality. One of the newer and more powerful tools is pipenv. Pipenv combines virtual environments and the familiar install capabilities of pip into a single set of command line instructions. It also utilizes Pipfile to lock down requirements, which we'll go over more later.
So within the Python ecosystem, how can we create reproducible environments? Well, it's recommended that at first you value innovation over stability. Because dependencies fixes bugs over time. It's always good to have the latest version of dependencies. And there's a natural tendency of software to become kind of stagnant over time. So while writing code, you should leverage Python's modular packaging and keep your dependencies up to date. So when Pygame updates, you pull the latest Pygame into your development environment. When SciPy updates, you pull the latest. When NumPy updates, you pull that, and SciPy again. So always keep your dependencies up to date to stay as far ahead of the stagnation as possible. And you can accomplish this with a requirements.txt file that looks something like this. You specify your two top-level dependencies, and you don't pin it. And because these aren't pinned, you always get the latest version by running pip install -r requirements.txt --upgrade. Or if you're using pipenv, you use something called a pip file. Pipenv provides a lot more additional capabilities, and you can see that in the pip file indicates where exactly requirements come from. So it actually tells you what repo. So you never run into the situation where you're pulling dependencies from two separate repositories. And it also keeps track of exactly which Python version a person is using. So this is great for the development phase. But once your code is ready for testing and deployment, innovation becomes risky, and you should be more concerned with stability. And to do this in Python, you should lock your requirements, your code, and all the dependencies. You can do this with a requirements.txt by piping the output of pipfreeze. Pipfreeze generates tells you the exact versions of your dependencies and the exact version of their dependencies that are installed. So you have your complete dependency tree, and you lock it down. And pipenv does something similar by using the Pipfile.lock. Again, it counts both than just using a regular requirements.txt. It tells you what Python version, the repository you're installing from, and the hashes of each dependency. And this is great because if you know that like installing the PyOhio distribution of some package break your system, you can pin the hash to a source distribution. You have a lot more fine-grained control with pipenv. But if you use this type of workflow, there are some questions you should ask yourself after you've released. How do you distribute your code? How do you promote your package from testing to production and ensure that the same bits with the same hash actually makes it into production? If you use PyPI, you can create a beta version, but when you're ready to create a production version, it and that usually means the package has a different hash. What happens if you need to update a dependency? Say a security fix was published for one of your dependencies, but your dependencies are pinned, right, for maximum stability. Do you have to repackage do you have to update that dependency in your requirements.txt file, repackage your code, and then like redistribute it again? So this has a lot of the same problems as a monolithic approach because you have to redistribute every time you update a dependency. And how do you guarantee the permanence of your dependencies? Most of the time, maintainers don't remove packages from PyPI, but what if they do? Like, what if left pad happens in the Python environment? And throughout all this, can you balance the amount of innovation in your code and the amount of stability?
Yes, you can. You can use Pulp. Pulp is a repository manager, and it's a tool that can help you with these problems. Pulp manages many types of content, from Python packages to generic files, container images, and Ansible roles. Pulp provides a general API to fetch, upload, organize, and distribute packages. Then, Pulp uses plugins to extend this functionality to different content types. In addition to the content types already mentioned, Pulp already has plugins for the following list of content types. If you don't see one that you want to use listed here, great news! You can build your own. You can create a new plugin because Pulp and its plugins are completely open sourced, and we would be happy to help you because it's a very welcoming community for that open source work. So how does Pulp work? Pulp organizes software packages into repositories. Once a repository is created, it is versioned, and these versions are immutable. When you add, remove, change any content in a repository, Pulp creates a new repository version while still keeping the old one. Both are still immutable and preserved so that you can go through and see the history of the changes you've made over time through this versioning. Once you have a repository version that you are happy with, it can be coupled with metadata, which could be appropriate to your plugin. For example, if the content type you're using Python packages, the Python plugin can generate a simple API or JSON API, which can be used for client package discoverability. A repository version and the associated metadata is called a publication. It's also immutable and also versioned. Pip can install a publication that is hosted by Pulp. So you still have the same install practice that you're familiar with. You just go pip install, but this time it is pointing at a repository or a publication that is hosted by Pulp.
So how does this help you balance innovation and stability? Recall that pinning requirements was how you gained stability at the cost of flexibility. Instead of doing that, Pulp allows you to curate your repositories, giving you full control over packages and their versions. So you have your code and your dependencies, and you're managing them in a single repository. You update your dependencies, and any client can update by pulling that dependency from the same repository. You don't have to re-release your package or alter your code in any way. So your requirements.txt will look like this. And this can be your testing requirements or your production requirements.txt. And you just point pip to the curated repository, and the right versions of dependencies and your code are all installed. This allows you to do some pretty nifty workflows. You can use curated repositories to develop in parallel, since repositories are versioned. You can pass a testing version to your quality assurance, say like version 5, while working on a new version, version 6, all the while there is an old version in production, version 4. And once quality assurance tests their version 5 and ensures that it works, they can and 5 goes into version 6 to QA, you start working on version 7. And since multiple publications can be hosted in parallel, you can keep innovating without affecting your stability. And if a publication has problems, you can always roll back to the last publication that's known to work. And Pulp can make this happen with 0 downtime. There's some other use cases for Pulp, and that includes creating a local mirror. You might want to do this because you want to conserve bandwidth if you're like out-of-the-way research station. You download PyPI packages once onto a local Pulp instance, And every computer in that research station can install packages from that in-network Pulp instance. You can also have a whitelisted index, and this is useful if you're working for the government and there's rules about what packages you can or cannot pull in from the Python package index. Maybe like a security department has to like validate all the packages before you're allowed to use them. So you can do this by running a PyPI mirror with whitelisted packages, so every package people install in that network has been verified. You can also use it for distributing your own software. Maybe you don't want to upload to PyPI or aren't allowed to. Pulp is a great way to share packages internally. And there's a couple of other repository managers up there. The two big names are Artifactory and Nexus. Pulp is written completely in Python, so you don't have to learn a new language in order to write a plugin. We're also free, free as in beer and free as in speech. And now that we've covered reproducing Python environments, let's talk about a couple of other things that are important to full-on reproducibility. Because the Python environment sits on top of your system environment. And system dependencies and system configuration also affects how your program behaves. And there's a lot of Python packages that have bindings to system code like glibc or OpenSSL. The first way is a virtual machine. A virtual machine is an ultimate monolithic package. And it comes with all of its downsides. It's large, it's opaque. If you need a new VM, how do you set one up? You better have really clear, precise instructions, and someone better follow those clear, precise instructions. A VM is a snapshot of a system at a point in time, so there are a couple of subtleties inherent with that. Because a virtual machine is an entire operating system, it can have running processes in the background that change its structure over time. So it could do things you don't tell it to, like auto-detect time zones or like auto-update packages. So there's a lot more variables inherent in a VM than you might think. One way to minimize the size and maximize transparency of a virtual machine is Ansible. Ansible is a tool that automates provisioning, configuration management, and setup. You can use it to create or recreate a virtual machine environment transparently and consistently, because Ansible can automate everything. With Ansible, you can install your system dependencies, you can set up your system configuration, you can install and configure your package, and you can install any and all Python dependencies. And an Ansible role looks something like this. So in this, we're installing glibc as a system dependency, and we're installing requirements into a virtual environment. Ansible, you can share your Ansible roles in this giant Ansible repository in this guy called Ansible Galaxy. It's like, but for Ansible roles. Unfortunately, the single repository architecture comes with a lot of the downsides of the single Python repository architecture. How do you curate your Ansible content? How do you promote your Ansible content from development to testing to production? And how do you control the level of stability and flexibility of your Ansible content? Pulp. With Pulp, you can manage your Ansible content. You can test your Ansible content, and when they're ready, you can publish your Ansible content, and you can have clients install it with Ansible client. Another way to create reproducible environments is through containerization. Containers are immutable system images. These are different from virtual machines. They're a lot smaller for one, and they're a single running process. So you eliminate a lot of the system services that can affect your environment. How do you manage your container images? Dockerfile is what's used to create your container images, and this ensures transparency. And Docker Hub, it's what's used to share your container images. And a Docker file can look something like this. So you have a base image, you're installing some kind of system dependency on top of that, and then you're installing your Python dependencies on top of that. Note that I'm not installing this into a virtual machine, and this isn't because I wrote a bad Docker file. This is because a Docker file is a process. So you should only have one project running on the Docker image at one time. If you have more than one, you should maybe resync that because Docker is designed to be single processes. And because it's single processes, you don't run into dependency conflicts. Therefore, you don't need a virtual machine. Virtual environment, my bad. And you can, so Docker Hub is what's used for sharing. It's a giant Docker repository in the sky, and like all mono repositories, it comes with some downsides. How do you curate your Docker content? How do you promote it from development to testing to production? How do you control the level of stability and flexibility? Pulp manages images too. With Pulp, you can manage your Docker content. You can test it all to the Docker client.
So in summary, creating reproducible environments is a complex dance between stability and innovation, seeking a balance throughout your development, review, and sharing processes. Some of the many tools available to you for accomplishing this with your Python projects include using requirements files with pip, requirements.txt files, as we discussed, which you can freeze, using lock files with pip-env to manage dependencies, Ansible's automation capabilities, and the powers of containers to limit variables within your system beyond the Python packages. There's also Pulp and other repository managers like it that provide additional flexibility to manage your workflows, allowing curation, rollback, and promotion through zero downtime. We hope that you're just as excited to use Pulp as we are so that your next project can have less problems with reproducibility. If you have any questions about Pulp in particular, you can check out our website, Pulpproject.org. We have links to documentation, YouTube demos. We have a very active set of IRC channels for both consumers and developers. We're very welcoming to first-time contributors, and we'd be happy to help you get started learning how to use Pulp or how to contribute your own additional plugins. You can also reach out to the Pulp team on Twitter or myself personally at CodeHealer. It's also my GitHub. If you have any other questions about this talk, feel free to catch us in the hall. We're going to have stickers. We have a slide share where you can see the slides again later if you had anything you wanted to revisit. And then PyOhio is obviously recording us, so there will be video afterwards. So please spread the word. If you like this talk, share it with others.
Thank you guys for coming.